In our last video, we learned about the cross product, which is a second vector multiplication. The cross product is only defined for three-dimensional vectors, and we saw this rather complicated definition, and we noticed that the cross product between vectors always results in a third vector. Geometrically, the cross product is a vector that is always perpendicular to both the original starting vectors. The direction that the cross product points is given by the right-hand rule. We have another relationship between the magnitude of the cross product vector, the magnitudes of the vectors themselves, and the sine of the angle between them given by this formula here. And we saw that the magnitude of the cross product vector is equal to the area of the parallelogram described by the vectors a and b. Let's work through some more conceptual examples. Take any two three-dimensional vectors a and b, and let's answer these questions. How do we know if a is parallel to b? Well, the classic method that we've seen is that a is a scalar multiple of b. However, there is a second way to check, which isn't as good, but it is true, so let's just write it down. Remember that the magnitude of a cross b is equal to the magnitude of a times the magnitude of b times the sine of the angle between them. If the vectors are parallel, that means that the angle between them is 0. And if theta equals 0, that means that sine of theta is also 0. So if two vectors are parallel, then the angle between them is 0, sine of the angle is 0. That means that the magnitude of the cross product is 0. The only vector that has a magnitude of 0 is the 0 vector. So another way to check if two vectors are parallel is to find the cross product. They're parallel if the cross product, a cross b, is the 0 vector. As we've seen, the cross product is a little bit tedious to compute, so I would not recommend this as a way to check if two vectors are parallel. The best way to check if vectors are parallel is to just see if one's a multiple of the other. But this will be true for parallel vectors. The cross product between parallel vectors will always be the 0 vector. How do we tell if two vectors are orthogonal or perpendicular? For this, we use the dot product. Two vectors are perpendicular if the dot product, a dot b, is 0. Remember that the dot product is a scalar, so a dot b equals the scalar 0. Cross product is a vector, and for parallel vectors, the cross product will be the 0 vector. Let's move on to example 5. Once again, we just have two 3D vectors, a and b, and we want to answer these questions without having to work through formulas for the dot product or cross product. We just want to think conceptually, geometrically, what are the different values here? First of all, what is another expression for a dot a? We've seen that a dot a is the same as the magnitude of a squared. This is true for any vector, 3D vectors, 2D vectors, any vector at all. It can be in any dimensions. The dot product of a vector with itself is the magnitude squared. What is the cross product of a vector with itself? How do we figure this out without working through a bunch of messy algebra? Well, any vector is parallel to itself. And if we take the cross product of two parallel vectors, we've seen that that cross product must be the 0 vector. So since a is parallel to a, then the cross product of a with itself is just the 0 vector. We don't want to write a cross a equals just 0 here, because 0 is a scalar. We really need to write down the 0 vector, 0, 0, 0. Now, question C. How does a dot b compare to b dot a? If you think of the formula for the dot product, if you switch the order of the two vectors, you're just switching the order of the multiplication inside the formula, and that doesn't change the answer. So for the dot product, a dot b equals b dot a. You get the same exact thing. How about the cross product? In the cross product, you get something different because of the right-hand rule. A cross b equals negative b cross a, as we've seen in a few examples. So you can switch the order of the dot product, you get the same thing. If you switch the order of the cross product, you get negative the vector of the cross product. Finally, how about part E? How can we compute this? This looks a little bit intimidating. Well, let's think of A cross B. That's the cross product. A cross B produces a vector which is perpendicular to both A and B. So in the parentheses here, I have a perpendicular vector to A and to B. I'm taking the dot product of this vector that's perpendicular to A. I'm taking the dot product of that with A. What's the dot product of two perpendicular vectors? It's just 0. So this will always be 0, no matter what the vectors a and b are. And this is a scalar because we're taking a dot product. And since a cross b is perpendicular to a, this dot product is just 0. Take a look at example 6. Let's take any 3D vectors, a, b, and c. They can be any three-dimensional vectors at all. And we want to think about these different ways of combining them. And we want to look and see if we get a vector or a scalar, or if the operation is actually undefined. With each of these different examples, we want to think of what sort of value we would get from these kinds of computations. So for the first one, 2, that's a scalar, and we're adding a, which is a vector. Can we add a scalar to a vector? No, we can't. We can only add two vectors together. 2 plus a doesn't make any sense. We could do a scalar multiple, 2 times a, but a scalar 2 plus a vector a, that's undefined. So here we have an undefined operation. How about part B? A cross parentheses b plus c. Let's work in the parentheses first. B plus c, these are two vectors, and this is vector addition. When you add two vectors, you get another vector back out. So we're finding A cross a vector. Is that valid? Can we do that? Well, sure we can. We're taking the cross product of a vector with a vector. That results in another vector. So the answer that we get here is a vector. How about part C? Once again, we want to start with the parentheses. B cross C is a vector. It's a 3D vector. The cross product always gives us a vector. So we have a vector in parentheses, and we're crossing that with another vector. Can we cross a vector with a vector? Yes, we sure can. And the result is another vector. Look at part D. Once again, take a look at the parentheses first. B dot C, that's a dot product. We can dot two vectors together, so this is fine. B dot C, that's a valid operation. But the result here would be a scalar. And we're trying to take a vector and cross it with a scalar. We can't do that. We can only cross a vector with a vector. So part D, this is undefined. How about part E? 2b is a scalar multiple of the vector b. So that's another vector. We have the dot product of a vector with a vector. Can we do that? Sure. And the dot product of a vector with a vector is a scalar. So the answer here is a scalar. Finally, letter F. We have a dot b. That needs to happen first. A dot b is a scalar. So we're trying to add a scalar to a vector. Oh, this is back to part A. We can't add a scalar to a vector. So letter F is again undefined. It's important to be comfortable with the different operations that we can do on vectors and what sorts of values that they give us. The dot product of any two vectors will always give us a scalar, and the cross product of any two vectors always gives us a vector. Let's conclude this section with problem 7. We want to find the area of the parallelogram determined by these two vectors, and we're going to do that using the cross product. Let's give some names to these two vectors. Let's say u is the first one, and it's 4i plus 2j minus k. And v, that's the second vector, that's I plus 3k. And I want to convert these to component form because that's what I'm more comfortable with. So the first one, we have an x component of 4, that goes with the I, y component of 2, that goes with j, and then -1 for the z component because we have a coefficient of -1 in front of the k. The vector v, we have a 1 for the x component, 1 times I. There's no j here, so 0 in the y component, and the z component is simply 3. So there's our vectors in component form. We want to find the area of the parallelogram determined by these two vectors. Geometrically, we saw that this area is equal to the magnitude of the cross product vector. So we want to find the cross product, compute the magnitude, that will give us the area of that parallelogram. Let's work through the steps. Once again, at this point, I encourage you to pause the video, try to compute u cross v on your own, and then compare to the answer that I get. Computing the cross product, we obtain 2 times 3 minus 0 times -1. Second component is 1 times -1 minus 4 times 3. And the third component is 4 times 0 minus 1 times 2. We're taking the magnitude of that vector, so let's simplify the vector and then find the magnitude. 2 times 3 minus 0 is 6. -1 minus 12 is -13. 4 times 0 is 0. Minus 1 times 2, that's -2. So there's our cross product. For the magnitude, we take the square root of the component squared. 6 squared is 36. 13 squared is 169. 2 squared is 4. Plug this into a calculator, and you get an answer of the square root of 209, which is approximately 14.5. So the area of the parallelogram described by these 3D vectors is 14.5. Let's use GeoGebra to visualize this. First of all, the vector u is 4, 2, -1. There's the vector u. And the vector v, 1, 0, 3. There it is. We want to find the parallelogram described by these two vectors. That parallelogram looks like this. There it is. And the area we just found, well, it's the magnitude of the cross product, and we computed that that's about 14.5. Notice off to the side that GeoGebra actually gives us that area, the 14.46. This is the magnitude of the cross product vector u cross v, and we can find that if we type in cross u comma v. That's exactly the vector that we found. We can see that it's perpendicular to both u and v with the direction given by the right-hand rule. Start our forefingers in the direction of the orange vector, that's u, curl toward the blue vector, that's b, and if we do that, then our thumb points in the direction of that cross product. We could also look at v cross u, and we get the same length vector, just in the completely opposite direction. The magnitude of that vector, u cross v or v cross u, is the area of the parallelogram described by vectors a and b.